Okay, so we're going to do question 8.10 now. So 8.10, we are having two players. One is the child and one is the child's parent. Okay, each of them is trying to maximize their objective function, where the child is going to be moving first and the parent is going to move second. Okay, so we have a sequential game with two players. That. Alright, so player 1 is going to choose. So player 1 is the child, and he's going to choose an action R in order to maximize his utility. Okay, so it's going to maximize the utility 1 by choosing an action R, where utility 1 is going to be a function of income y1, and y1 is just a function of R. Plus the amount of L that is given from the parent. Okay, so player 1 is going to choose R in order to maximize this objective function. So and he's going to be the first mover. So he's going to move first. Alright, now for the parent, they are player 2. Okay, so they are the second mover. Okay, so they are going to choose an amount of L they would like to give to their child in order to maximize their objective function. Now the objective function is going to be the function, the utility 2, which is their utility as a function of the income y2 that they earn, and this is going to be a function of the action chosen by the child earlier, okay, action R, minus the amount of L they already given to the child, and because they also care about a utility for the child, so the objective function is they also want to maximize part of the child's utility. So it's going to be plus alpha utility 1. Okay, and we know that utility 1 is a function, is the utility of the child, which is a function of income, y1 as a function of R plus L. Alright, so player 2 is going to maximize that objective function by choosing an amount L they would like to give to the child, would like to give to player 1. Alright, so now we have a sequential game. When we have two players, we are going to use a backward induction method, where we are trying to find a solution for player 2 first, and then plug the solution into the function for player 1, and then we'll try to maximize the objective function for player 1 by choosing an amount R. Okay, so using a backward induction method, we are going to solve for the player 2 first. Okay, so player 2 first. So player 2 again trying to maximize the objective function by choosing an amount of L, where objective function is the utility for player 2, which is a function of income y2 as a function of R minus L plus alpha u1 as a function of y1 and L. Alright, so now to maximize the problem, we just have to find a first order condition, where we just have to differentiate the objective function over here with respect to L. Okay, so now if we're looking at this, we do not have an explicit function for the utility, so therefore we will just have to implicitly differentiate. Alright, so if we're looking at this one, u2 is a function of y2 and L. So when you differentiate this, we basically have to apply the chain rule, where we differentiate the utility 2 function with respect to everything inside a bracket, and then multiply by the differential of everything inside a bracket with respect to L. Okay, so I'm just specifying the rule over here. So applying the chain rule. Now the chain rules is if you have if you have u as a function of f and f as a function of L, for example, okay, and if you want to differentiate u with respect to L, so if you want to differentiate the outside function over here as a function with respect to a little variable inside the little bracket over here, that is going to be equal to u dash of f times f dash of L. Okay, so that's the chain rule. So what we do over here is we differentiate the whole utility function with respect to everything inside the bracket, and then multiply by the differential of everything inside the bracket with respect to little variable L over here. Okay, so we apply exactly the same thing here. We treat everything inside the bracket here as a function of L. Okay, so it's basically as an f of L. Alright, so we're treating this as a function of L. So when we differentiate that, this thing over here with respect to L, that will just become U2 dash, which is a differential of a utility function with respect to everything inside a bracket. Okay, so basically we keep everything inside a bracket same, and then we multiply by the differential of the function inside a bracket with respect to L. Okay, so when I differentiate a thing inside a bracket with respect to L, I can see that the differential of y2 with respect to L will just be equal to 0 because y2 is independent of L. And if I differentiate negative L with respect to L, I will get negative 1. Okay, so I get negative 1 over here. And that is how I apply the chain rule to find the solution. Okay, so very similar for the next one over here, where I have utility1 as a function of y, 1, and L. Okay, so if I treat everything inside over here as a function of L again, then I would have alpha u dash 1, which is the differential of utility with respect to everything inside a bracket. So that's just y1. So u dash of 1 as a function of y1 plus L. Okay, times the differential of everything inside a bracket with respect to L. So if I differentiate y1 with respect to L, that becomes 0. Okay, because it's independent of L. And if I differentiate L with respect to L, I get 1. Just 1 over here. Alright guys, so now remember, don't get yourself confused. So this is U2 as a function of everything inside a bracket, and U1 as a function of everything inside a bracket. Okay, so it's not a multiplication sign over here. Alright, and I would like to make this thing equal to 0 because that is my first order condition. Alright, so if we're looking at the star condition over here, we can see that the differential, the utility 2 is just a function of y2 and L, and y2 is just a function of R, and utility 1 is also a function of y1, and L where y1 is also just a function of R. So if we have an explicit function for y2 and utility, then the star condition over here is just basically an equation between L and R. Okay, so it should be able to find, it should be possible to find L as a function of R. So since we don't have an explicit function for y2 and u2 and u1, however, we can see that implicitly by solving this equation star over here, we should be able to find L as a function of R. Okay, so implicitly L is going to be a function of R. Okay, so I'll say L star. So if I'm solving the star equation over here for the values of L, I should be able to find L as a function of R. And I call that L star because that is the optimal amount of L that the parent is going to choose in order to maximize the objective function. Okay, so I don't know the explicit form of L as a function of R. However, I know that implicitly the optimal amount of L is going to be a function of R if I'm solving the star equation over here. Alright, so if I substitute L star back into the star equation, then it should satisfy the star equation. Okay, because it's just the optimal amount of L that I should be able to find from the star equation. So if I substitute it back into the star equation, it should satisfy the equation. So what I'm going to have here, I got u2 dash as a function of y2 as a function of r minus L star as a function of r. Okay, I basically repeat the star condition, so I rewrite everything. However, I just substitute the values on. So instead of L over here, I put L star as a function of r, because that is what I can find from the star equation. Okay, so it basically there's nothing changed over here. I just rewrite the star condition. However, implicitly indicate that I know that L is a function of r. Okay, so I got -1 over here plus alpha u1 dash y1 as a function of r plus L is a function of r. Okay, and that has to be equivalent to 0. Okay, so if I implicitly differentiate this function, the above equation, okay, so the above identity with respect to r, then I will be able to get -u double dash 2. Now again over here, what we do is we applying the chain rule again. So I would like to differentiate the whole thing over here with respect to a little r inside a little bracket. Okay, so the chain rule over here is you treating everything inside a big bracket as a function of r. Okay, so when you differentiate, it's going to be the differential of the big utility function u2 with respect to everything inside a bracket, multiplied by the differential of everything inside a bracket, which is the differential of f with respect to r. Okay, so we are going to get negative. So if I differentiate the big u2 dash over here, I get u2 double dash. Okay, and everything inside the bracket stay the same. So which is y2 as a function of r minus L as a function of r. Okay, times, so now times the differential of f with respect to r. Okay, so now if I differentiate everything inside a bracket with respect to r, I can see that y2 is a function of r. So if I differentiate that, it's become y2 dash as a function of r minus L star, I know is a function of r, so when I differentiate it, it's become L star dash as a function of r. Okay, so I'm done with the first part. I'm going to do the second half. Again, exactly the same, where I'm treating everything inside a bracket over here is a function of r. Okay, so if I differentiate with respect to r, I will just have to use the chain rule where I differentiate utility u1 dash with respect to everything inside a bracket. So that will become alpha u1 double dash, everything inside the bracket stay the same, so which is y1 r plus L star r. Okay, now remember, this is just basically means u1 double dash as a function of y1 and plus L star. Okay, so it doesn't mean when we multiply over here. So it's just a function. So u1 dash as a function of these things. So when we differentiate, this become u1 double dash as a function of these things. Okay, multiplied by the differential of everything inside the bracket with respect to r. So if I differentiate y1 as a function of r with respect to r, I get y1 dash as a function of r plus L star as a function of r. I differentiate that, it's become L star dash as a function of r. Alright, and everything will still have to be equal to 0. Okay, so now what I want to find is I want to find L dash of r. Okay, so basically L star is the optimal amount of L that I would like to find, and I know it is a function of r. So so what I really want is the differential of L star dash of r. So I'm just rearranging my equation in order to find L star dash of r. Okay, so if I expand everything, now this thing over here, it just basically means u2 double dash as the functions of everything inside. So instead of rewrite everything, which is a bit long, I will just leave it like a bracket. Okay, so I will just leave it like this. So you know that everything inside a bracket is going to be this part over here. Okay, so it just basically means u2 double dash as the functions of everything inside. So I'm not going to rewrite everything because it's taking a little bit of time. And it becomes messy later when you have a lot of expressions. So I can just leave it in the short form like this. Okay, so if I expand this bracket over here, that's become negative u2 double dash times y2 dash. It's a function of a minus. So minus become a plus u2 double dash. So I'm not going, as a function of everything, I'm not going to rewrite that. Multiply by L star dash as a function of a. Okay. Plus, now over here I'll do exactly the same thing. Alpha u1 double dash as a function of the thing inside. So I'm not going to rewrite it. And multiply by y1 dash as a function of a. Plus alpha u1 double dash as a function of everything inside, multiplied by L star dash as a function of a, and it has to be equal to 0. Okay, so I expand the bracket over here and the bracket over here. Okay, so like I said before, this is the thing I want to find and this is the thing I want to find. So I just factorize it and put them in together. So I got u2 double dash plus alpha u1 double dash, everything multiplied by L star dash as a function of a, and I move everything else that doesn't include L star dash of to the right hand side of the equation. So that's become u2 double dash times y2 dash of a minus alpha u1 double dash times y1 dash of a. Okay. So therefore, L star dash as a function of a is going to be equal to u2 double dash y2 dash of a minus alpha u1 double dash y1 dash of a, everything divided by u2 double dash plus alpha u1 double dash. Okay, so we are going to see in a little while why we have to find the values of L star dash of R. Okay, so because we need to substitute back into the first order conditions for the first player. Okay, so we just leave it at this point first, and then we are going to see where we are going to use it. Okay, so we're done for player 2. We are now going back to player 1, and we try to find the option. We try to find the optimal amount for the child. Okay, so the player 1, what he wants to do is to choose the amount of R in order to maximize the utility 1, which is a function of y1 as a function of R plus the amount of L that the parent is going to give to him. Okay, now being a first mover, he should be able to take into account the optimal amount of L chosen by his parent, and then he can decide how much R he's going to pick. Okay, so he knows that his parent optimal amount of L is going to be a function of the R that he's going to choose. Okay, so he is going to take that into account and choose the amount of R in order to maximize the utility. Okay, so it's basically just similar to a sequential stack caboose game where the player 1, which is the first mover, taking into account the fact that the optimal amount chosen by the other player is going to be a function of the choice by the first player. Okay, so player 1 knows that. Okay, so player 1 takes into account the fact that his parent is going to choose an amount of L star as a function of R. Okay, so therefore he is going to maximize the utility function by choosing R, knowing that the amount of L over here that his parent is going to choose is going to be the function of his choice. Alright, so the problem becomes maximize a utility function by choosing amount r, where the utility 1 is a function of y1 as a function of r, plus L over here, we know the player 1 knows that it's going to be the optimal amount chosen by his parent as a function of his choice. Okay, so L over here is the amount that's going to be chosen by the parent according to the amount, the decision, the action R chosen by the player 1. Okay, so when we differentiate by the first order condition, we would like to differentiate the objective function with respect to R. Okay, so now again, when we differentiate, we're treating the whole thing over here as a function of R. So we're applying the chain rule again, where we differentiate utility U1 with respect to everything inside a bracket, and then multiply by the differential of everything inside a bracket, which is F with respect to R. So that is going to become U1 dash, everything inside a bracket, which is Y1 plus L star R. Okay, so U1 dash as the functions of everything inside a bracket, multiplied by F dash of R. So when we differentiate everything inside a bracket with respect to R, we are going to get, so if we differentiate Y1 as a function of R with respect to R, we get Y1 dash of R. We differentiate L star as a function of R with respect to R, we get L star dash of R. Okay, so now you can see the purpose of us trying to find L star dash of R earlier. Okay, so that because we want the function for it in order to substitute the function into here. Okay, and first order condition, therefore we would like to make this equal to 0. Alright, so now from the double star equation above, we know that we found we found the L star dash of R. Okay, so substitute the values of L star dash of R into outside this is the 3 star condition. Okay, so use the function that we found for L star dash of R from the 2nd star condition, substitute that into the third into the 3 star condition. We are going to get U1 dash. Now instead of writing everything over again here inside a bracket, again I will just do a dot. Okay, so we know that it is U1 dash of everything over here. So I wouldn't want to rewrite everything, so I just put a dot over there. Okay, so multiply by Y1 dash of R plus L star dash of R. Now L star dash of R we found earlier equal to this, so I will just rewrite everything over there. So that's equal to U2 double dash times Y2 dash of R minus alpha U1 double dash Y1 dash of R, and everything divided by U2 double dash plus alpha U1 double dash. Okay, so that's the expression we found for L star dash of R. So I just substitute it to here. So I use a big bracket for this. Okay, and that will have to be equal to 0. Alright, so from here, I would like to simplify this thing a little bit. So I'll see what I can do about this. Okay, so if I so I put U1 star here, and if I try to do the common denominator for a thing inside the square bracket, that will become Y1 dash of R multiplied by U2 double dash plus Y1 dash of R times alpha U1 double dash. Okay, and then plus everything over here. So that's become u2 double dash y2 minus alpha u1 double dash y1 dash of r, and everything, sorry, okay, everything divided by u2 double dash plus alpha u1 double dash. Okay, and everything still have to be equal to 0. Alright, okay, so I am going to get u1 dash divided by u2 double dash plus alpha u1 double dash. Okay, so if I move this denominator to outside the square bracket, inside the square bracket, I am going to have, okay, so looking at this one, I can see that maybe I can factorize something a little bit. So I got u2 double dash over here, and I got u2 double dash over here. So if I take it out, I get u2 double dash times y1 dash as a function of r plus y2 dash as a function of r. Looking at the second and the fourth terms, I can see that I got alpha u1 double dash as a common factor. So if I factorize it, I am okay, sorry. So this the second one and the last one is exactly the same. Okay, so okay, so this one we can just cancel with this one. Okay, so they're exactly the same thing, so they just cancel out, and this is it. Okay, so that becomes 0. Okay, so what I got over here is that, so if I take the u2 double dash outside the square bracket, I got u dash times u2 double dash divided by, sorry, u2 double dash plus alpha u1 double dash, and inside the square bracket I got y1 dash of r plus y2 dash of r, and it has to be equal to 0. Okay, so this condition being equal to 0 basically implying that y1 dash of r plus y2 dash of r will have to be equal to 0. Now this is happening because everything over here is going to be different from 0. Okay, so u1 UTD, if you differentiate it shouldn't be equal to 0. Okay, so the utility function, you differentiate first, and if you differentiate twice, it cannot be equal to 0. Okay, so therefore in order for the whole thing to be equal to 0, the thing inside the square bracket will have to be equal to 0. So that basically means the child is going to choose an amount of r satisfying this equation over here in order to maximize the objective function. Okay, so this is going to be the condition for r. This is going to be the amount for r that the child is going to pick in order to maximize the objective function, or to maximize the utility one. Okay, so outside this is the star condition. Okay, so the star over here implies, okay, or the star over here is implicitly defines, okay, the optimal amount of r that is picked by player 1 to maximize his utility. Okay, alright, and the question wants you to show that this amount is going to be the functions of the income of both the parents and the child. Okay, so now if we can see that the sum So the sum of the child and the parents income is y1 plus y2. Okay, so where y1 is a function of r and y2 is a function of r. Alright, so if the child is picking an amount of r in order to maximize this objective function over here, then the first order condition is going to be the differential of this function, this objective function with respect to r. So it's going to be y1 dash of r plus y2 dash of r equal to 0. Okay, so if you compare the star conditions over here and the conditions over there, they're exactly the same thing. Okay, so I'll say this is the double star. So it basically means the optimal amount of r that the child was picking over here to maximize his utility turned out to be exactly the same amount of r that he is going to pick if he is maximizing the income of himself and the income of the parent. Okay, so even though he doesn't have an intention to maximize the income for the parent, he somehow end up doing that because the income of the parent is going to affect the amount that they are going to give to him. Okay, and he cares about that. So what we did over here shows that the amount of r that the child is going to pick to maximize his utility is going to be the same as the amount of r that he is going to choose if he was to maximize the utility, to maximize the income of the parent and of himself. Okay. Right. So since the star and the double star are identical or are the same, that basically means the child or the player one picks an optimal amount of r that is equivalent or that is identical, that is the same as if he was maximizing his and his parents' income. Okay.